Hello, and welcome to the history of the atom check. And I'm firstly going to be taking you through the time before modern chemistry, before leading on to the solid sphere model. So, back before modern chemistry, not a lot was known. A few philosophers had tried to come up with the ways of describing atoms, but most at the time believed that everything was made of elements, not the elements we consider today, but instead earth, water, fire, and air. Aristotle specifically furthered this by saying that everything was also made of a thing called ether, and Democritus was kind of pushed aside as being a liar or just being. In 1766, John Dalton was born. He grew up to a Quaker family and became interested in meteorology from an early age. And as he got older, he managed to record daily weather patterns for part of his research, which eventually led him into chemistry. Before publishing his atomic theory in 1808, though, many chemists of the time believed in strange theories, one of which included phlogiston. He, alongside Antoine Lavoisier, are considered to be the fathers of modern chemistry. Dalton's theory revolves mainly around the fact that everything is made of the indivisible atoms as proposed by Democritus. He thought that atoms lied next to one another to form molecules, and they underwent no physical change. His basis for this theory was behind Lavoisier's law of conservation of mass, which meant that the mass of the reactants is equal to the mass of the products. The only problems with his theory, though, is the fact that there is little experimental evidence. The thing is with his the time is that they didn't have the greatest of instruments to record things. However, he was still pretty good. He managed to say that oxygen was 8 times heavier than hydrogen, but some of his work wasn't the best. He thought that water was simply OH and not H2O.
Hi, I'm Alex. I'll be talking about the plum pudding model. The model was discovered by J.J. Thomson in 1904, and he said that corpuscles, or electrons, were arranged non-randomly in rotating rings and were surrounded by a soup of positive charge. He also had a previous model which he disproved himself. The nebular atom hypothesis he came up with was, according to him, composed of immaterial vortices. He disproved it due to lack of information on charges. Experiment using Crookes tube, which is a sealed glass container with 2 electrodes on each end, sealed by a vacuum. The tube generates cathodes and when voltage is applied, and the observations made were that rays can be deflected by electric and magnetic field. J.J. Thomson discovered that corpuscles, or electrons, weren't made of light but were charged particles. This is how J.J. Thomson came up with the plum pudding model. That model is that it demonstrates that atoms possess a uniform positive background charge, which isn't true. Geiger and Marsden disproved the model using a splitting pattern experiment, which basically used a fluorescent screen and a gold foil. If the plum pudding model was correct, the electrons should have passed straight through the foil in a straight line. However, the reality was that the electrons scattered around the place in no particular pattern, and Abdullah will talk to you more about that.
Hi, this is Abdullah. The Rutherford model of the atom, named after the New Zealand-born physicist Ernest Rutherford, was directed under the famous Geiger-Marsden experiment in 1909, which suggested, according to Rutherford's 1911 analysis, that J.J. Thomson's so-called plum pudding model of the atom was incorrect. This experiment, known as the golden foil experiment, Rutherford fired a thin beam of alpha particles at a very thin sheet of pure gold. Alpha particles are helium nuclei that Ernest Rutherford discovered positive radioactive emission in 1899, and they are given off in various radioactive decay processes. In this case, Rutherford placed a sample of radium inside a lead box with a small pinhole in it. Most of the radiation was absorbed by the lead, but a thin beam of alpha particles escaped out of the pinhole in the direction of the gold foil. The gold foil was surrounded by a detector screen that would flash when hit with an alpha particle. The use of was not an arbitrary choice made of Rutherford. Gold is an incredibly malleable substance, which means it can be hammered into extremely thin sheets. A foil this thin was necessary for Rutherford to carry out this experiment successfully. If it was any thicker, the alpha particles may have not been able to penetrate it. The results were that, while almost all alpha particles passed straight through the gold foil, a few particles were deflected more than 90 degrees from their path. It was concluded that, from this experiment, that the positive charge must be localized over a very tiny volume of the atom, which also contains most of the atom's mass. This explained how a very small fraction of the alpha particles were deflected drastically. Presumably, this is the case due to the rare collision with a gold nucleus. Since most of the alpha particles passed straight through the gold foil, this led to Rutherford to conclude that the atom must be made mostly of empty space. The main problem with this model is that the orbiting electrons are moving charges and should radiate electromagnetic waves, which according to electromagnetic theory causes the electrons to lose energy. This loss of energy would cause them to spiral into the nucleus. In other words, there was no way of explaining why an atom with an orbiting electron is stable and stayed orbiting the nucleus without collapsing into the nucleus. Once Niels Bohr modified this view into a picture of a few planet-like electrons for light atoms, the Rutherford-Bohr model caught the imagination of all. It has since been regularly used as a symbol for atoms and even for atomic energy, even though this is more properly considered nuclear energy.
I'm Dominic Conway, and I will be explaining the planetary model. Niels Bohr was born in Copenhagen in 1885. He added to the previous nuclear theory of the atom by Ernest Rutherford by adding Planck's quantum theorems to form the new planetary model of the atom. In the it stated that the nucleus was a small, dense, positively charged area at the center of the atom, with the negatively charged electrons orbiting the nucleus in fixed orbitals. This is similar to how the planets orbit the Sun in a solar system. The electrons can be promoted to a higher energy orbital by receiving energy. This is known as atomic excitation. When the energy is lost, the electron is demoted to a lower energy orbital. This is atomic de-excitation. Similar to the planets orbiting in a solar system, it is not exactly accurate, as electrons are quantum particles but do not orbit in a singular plane like planets do. This is due to them behaving as both a wave and a particle. This is known as wave-particle duality. Also, the force that attracts electrons to the positively charged nucleus is the Coulomb, not gravity as in the solar system model.
Hi, I'm Albor. I'm going to be talking about the quantum model. The quantum model was invented by Erwin Schrödinger, an Austrian physicist, in 1926. What Erwin did is he took the Bohr planetary model and made it one step further. This model is based on quantum physics, hence the name, and its improvement of the previous model. The quantum model is used for observations of complex atoms. This is portrayed as a nucleus surrounded by an electron cloud. Because of this, the sublevel concept was introduced, making it easier to identify the location of where the electron is going to be. This model is the only model which associates with light being both a wave and a particle. The model shows that electrons do not flow in a certain order. However, there's a few problems with the model, like it doesn't not predict the exact location of the electrons or the path of the electron, just the odds of where the electron is going to be. And also it makes it really hard to actually understand the concept of this model. This concludes our presentation for the models of the atoms.